So that always makes things nice. Apologies for the delay, people online. I am using the internet. The Wi-Fi is being uncooperative today. So to that end, I am using my phone's hotspot, which means who knows how good this will be. Or bad, depending on your perspective. And also how much data it'll use. That'll also be interesting. I don't know. Maybe I'll try switching to the Wi-Fi at some point and destroy everything. Who can say? So, now that the stream is working, so regarding the test, fairly happy with that. It was okay. So the average, I think, ended up being like a 60. Actually, I can just straight up tell you all what the average is. Let me give you the exact number. The average was 62.4, which is lower than the first one. The first one, the average was a 66, so a little bit lower. There were 2 questions from so remember this test, we're using some of my stuff from last year. So there's 2 questions from last year that a lot of people didn't score well on. And I tried to reword them, but people still did really bad on them. Like 30% of people got them right. So those 2 questions, I will go over after this week. I'm not going to say what they are now because I have people still doing makeups and things like that due to medical emergencies or things like that, things that fall within the exemption policy. But I will go over those, what they are, and I can I can guarantee you problems like that will show up then on the final because they are relevant questions. And so at the end of the day, what I care is that at the end of this course, you know what's going on. So, I mentioned that. I'll talk about those next week, what exactly those questions were. But there's a couple of those, and then there was like 2-ish more that were kind of like, below 50%. So based on that, I decided on the 13-point curve, which also conveniently brings it up to a 75 average, 75% average. But really, that wasn't the goal with the curve. The curve wasn't to bring it up to a certain percent. It was based on how people responded to the questions. And so giving points kind of based on how many questions were there that people didn't do well on. Not necessarily giving all the points for those questions, because some amount of people got it right, but giving some percentage of that. And I kind of came out to 13 points after doing some consideration. So when I think, again, just to remind you, when it comes to curves, my goal with this class is not for the class to have a certain grade at the end. The goal of the class is for you all to have a certain level of understanding at the end. And to that end, when I do a curve, it's based on I am the only common denominator in this entire class, so I look at the questions that everyone did bad on, and that's reflective that I did not prepare you all well for those questions. That's how I gauge a curve. A curve is not based on, it's based on more of where did I fall short kind of thing, which is then reflected in how people did on certain questions. So, anyhow, again, next class, I will show the grade distributions. You kind of, I think, can see some of it on web courses, but I'll give you all a nice histogram because it's always nice to know how you pair up to other people. But same rules as last time. If after the curve you're above a 60, that means you have some level of understanding that's like acceptable, okay, something like that. The higher you are above a 60, kind of the better and better you get. Once you get above an 80% means you have a decent understanding. And then above a 90 means you have like a really good understanding and so on and so forth. Subsequently, below a 60 means that this is an area that needs some improvement. So go through, try to think about what questions you can come by my office hours next week if you want to see what you got on the test. And I can kind of show you which questions you got wrong and can go over that during office hours. So feel free to stop by and I can do that. Yeah, just kind of think through what questions did you struggle with. Those are good ones to look through because the final is cumulative. So, speaking of the final, this is just good to kind of talk through right now. So the final, and I'll kind of show you all this in 2 ways. So this is in the syllabus. In the syllabus, I did put the final. But in case you're curious, how do I figure out when the final is? I don't decide that. I don't decide when the final is. I have zero control over when the final is. But the reason I mention that is if you're curious when any of your finals is. If you just look up UCF final exam, this is how I figured out when your final exam was. They didn't send me an email or anything. I went to this website where anyone has access to it. So this is from UCF. So they make an exam structure based on when the classes are, with the intention being that you don't have a ton of exams on the same day. I think their overall goal is that you don't have like 3 exams in the same day. If that happens, I don't know exactly what to say about that or anything, but that's their goal. They're purely basing on, hey, we don't want to have exams overlapping, and we can't have conflicts, so they can't have you having 2 exams across the same time. And they also want to try to reduce how many exams you have. So our class meets on Tuesday, Thursday. Our class starts at 4:30. Our class ends at 5:50. And bam, that's our exam time and day. And that's in the syllabus as well. So I didn't have this at the very beginning of the year because they didn't have this set up at the beginning of the year. But a week or 2 later, I did add it to the syllabus. So Thursday, April 25th, 2024 is at 4 p.m., not 4:30. So our class is normally at 4:30. The exam starts at 4. Again, I don't decide these things, but you should have no other class conflicts, so make certain you all block this time out. So 4 to 6:50. It is 2 hours and 50 minutes. That is a lot of time. And I'm going to straight up tell you all, I am not designing a test for 2 hours and 50 minutes. I am more so planning a test around 2 hours. So I say that you will have the full 2 hours and 50 minutes. So let me make that clear. You will have from 4 to 6:50 p.m. to take this exam. But I'm not designing this test to fill that entire time. So that means there's a lot of buffer time to check your work, to go slowly. I don't want you all to be racing through this. This is the final test of what you understand. It's cumulative, so I am designing this so that it's not a marathon per se, but it's kind of a, hey, this is your chance to have as much time to kind of show what you know. It is going to be all multiple choice because the grades are literally due 8 days after this. Grades are due for me, I have to submit the grades 8 days after this. So there's no way we can have free response grades graded in 8 days in a satisfactory manner. So it's all multiple choice. It'll be about 40 questions, somewhere between 40 and 50. So I'm going to look it over. Again, the goal is to have the breadth and depth of this course. So to kind of, just like the multiple choice questions you've been having, have stuff like that. There may be a few multiple choice questions that are a bit more in depth to account for not having a free response portion. So there may be a few that are a bit more involved than the ones up to this point. I say that, again, it'll be nothing more difficult than I've given you on a test. It will not be I will not give you a multiple choice question that is like one of the full free response questions we're giving. But it will be maybe a little bit more steps than the multiple choice up to this point. Not all of them, but just a few more to account for not having free response. So I still need to cover that depth of understanding, meaning be able to do 2-step, 3-step problem kind of things. Again, 40 to 50 questions covering everything in this class. So everything from test 1, everything from test 2, and then the stuff we're covering this week and next week. So electromagnetic waves and lenses. This is worth 30% of the grade. This will replace your lowest test grade if it is higher than your lowest test grade. So let's just make up some numbers to make this abundantly clear. So if test 1, I'm just going to make up grades. Let's say on test 1, you scored a 70. In test 2, you scored a 60. And on the final, let's say it went really bad and you scored a 50. It will not replace either of those grades. It's not going to replace the 60 or the 70 because those are higher. Now, let's say on the final you scored a 70. That will then turn this 60 into a 70. Now, I say all of this. You may or may not see this in web courses. You may or may not see this. I'll have to decide. I will probably try to make it happen where you can see that change in web courses. That I would probably try to do. So I will adjust the grades. I'll adjust your test 2 grades. And in this scenario that I gave right here, where test 2 is the lowest, it will replace the entirety of test 2. The free response and the multiple choice together. It will replace that entire grade. So it won't just replace a piece of the test. It will replace the entire test. So this is something I manually have to do. So after your all's test, again, same thing as usual. By the end of that weekend, my hope is to have that graded and have kind of all of that done, have even the lowest test grade kind of replaced. That will then be reflected in web courses. Everything should be there at that point. All the quizzes will be adjusted, all the clicker questions, everything. I say that with the caveat, there is nothing extra at that point that can be done about your grades. So literally, I am just going to post those grades in web courses so you can confirm that everything looks the way it should. If at that point you're like, my grade's not what I want to be, there's nothing I can do unless I made a mistake, unless something is incorrect. So that's something that I'll clarify that as well. So if you're like, oh man, I'm so close to this, is there anything? No, there's nothing that can be done at that point because it wouldn't be fair to everyone. Any opportunity I gave, I'd have to give to everyone. And at that point, no, I'm not going to scramble and try to make something happen. So we got a few more weeks. Take advantage. Make certain you're kind of doing all the things. The physics I care about number 2 is due by the end of this week. That's an easy kind of assignment thing, so don't forget to do that. Physics I care about number 2. Pick something. Explain how it works. Make certain you're actually put a little bit, like it doesn't take that long. You can put kind of as much time. I don't want to say as little time. Make certain you spend some time on it. Don't just copy it. Obviously, it's going to sound obvious, but just to make sure. Don't just copy and paste things. Don't just have ChatGPT write a thing. Literally, this does not take that long. Even if you just put like the minimum amount of effort on your end, 15, 20, like lookups, learn something about how stuff works in a field that you're interested in. It's easy points, but I do also want you to get some benefit from it. I don't want it to just be busy work. That's not the point of it. The point of it is to have something that connects to your interests and also be some easy points. But I don't want it to just be an assignment for the sake of an assignment. So spend a little bit of time on that, and double check after you turn it in. I believe it'll tell you. I'm not 100% on this, but there's the whole turn it in thing that checks plagiarism, all that jazz. Make certain it's not flagging you for any, does it show you all? I honestly don't know. Yeah, make certain it's not flagging is that you literally copy and paste it, because that means I will literally see that it's copy and paste. So, anyway, obvious things, but just important to clarify. And I think that's kind of largely it. At this point, your all's grade is accurate up to this point. If the discussion sections and stuff haven't been graded, that's the TAs, and I'll have to check in on that. But as far as all the grades that were in there that I could play around with, all the quizzes were moved to the adjusted quizzes. So instead of being graded out of 4 points, or out of 5 points, they're graded out of 4.5. That benefits you all. The clicker questions, I synced those over, and I score those, whatever number, I think it was like 90-something questions I asked. I don't grade it out of 90-something points. I grade it out of whatever points it is, such that if you got every single question correct, you answered every single one, you have 125% in that category. That's to account for, remember, 25% is getting the question right. So there's and also if you miss classes, whatever. So that's in there. So that's adjusted for that as well. Everything's there, except the free response for test 2. That is literally the only grade that is missing, with maybe some exceptions with discussion sections if they haven't done things. So look it over, see how it's going. Ask me if there's any areas you feel like you need to shore up on, do what you need to do there. My office hours, help room, SARC, all those things. All right, any comments, questions? Yeah.
Is there any chance for like an exemption on the final or no?
There is no exemption because the final is cumulative. So there's stuff that's going to be on the final that has not been. So the question, just so everyone can hear it, is there any chances of the final being exempted and being able to skip it due to other grades? In this class, there is not, because the final is cumulative. And so there's twofold to that. One, we got 2 weeks of stuff that I haven't tested you on. So that's going to cover that as well. But more importantly in my mind, I want your all's grade in this class to be reflected that at the end of this class, you understand the breadth of the class. And to that end, the final is like the last time I kind of see you all. So the goal is at the end of the class that you actually know all the things in the class. And it wasn't one of those you learned it for like 3 weeks and now it's gone. The idea is by the time you leave my class to assess, do you know the stuff by the end of the class? All the stuff in it. Because, in my opinion, that's it's not fun. Cumulative finals suck. Like, I hated cumulative finals, but teaching philosophy-wise, if a class is supposed to teach you a certain amount of material, then the idea is at the end of that class you know that material. And unfortunately, a cumulative final is the only way to really assess that. So that's why that's there. Because I get it, y'all. 3 months after this class ends, if this was me, if I was in your shoes, I forget things 3 months after I've used them. But the goal is at least by the end of this class that you remember it by the end of it. Whatever happens after that, that's out of my hands. If you need it, you'll remember it. If not, whatever. So anyway, it's a good question. Any other questions about any logistics, final, grades, yada yada?
Finals in this class.
Yes, yeah, that is a great question. The final is in our normal room, in person only. It'll be in here just like all the other tests. And again, the structure will be basically, the Scantron will be there. Oh, there is one last detail. So the structure will be the same in that the Scantron will be there. The questions, all the same formatting that you're used to. The one difference with the final versus the others is you don't get a 5x8 note card. You get an entire sheet of paper, front and back, whatever you want, because that's equivalent to 2 5x8 note cards. And the final is everything in the class, so I give you twice as much room. So I'm not going to give you all 5x8 note cards because you just get a blank sheet of paper, put whatever you want front and back on it, as long as it's not a flip notebook kind of thing. And again, it ends up being the size of 2 5x8 note cards. So it's nice. Saves me money, also gives you all more room. You can type stuff and print it out, do whatever you want on that thing. You will have the formula sheet as always. Yeah.
Could we use our 2 5x8?
You can. The only thing you'll want to make certain of, you can. So the question was, can you just use the 2 5x8 note cards? Totally. If you really like your note cards, you felt like they had everything you needed, yes. But they will be missing this 2 weeks worth of content, so you just need to make sure you have space on there for that. If you're afraid of having space, one thing you can do is take a picture of those note cards, put them on in Word. Put them on that paper, squish them a bit, give yourself a little bit more room, and then print the paper. That also works. So I don't care what's on your note card. Put whatever you want. Put I love physics in all capital letters and take up the whole paper with it if you want. Or I hate physics. I don't really care. Put whatever you want on it. And again, you can print it, colors, all that stuff, as long as it's not a bunch of loose papers. And as long as you're only using your note card and you're not sharing it with someone else, just because obviously that runs into problems. So, it's a good question. Anything else? All right, y'all. Final stretch. 3 weeks left of having to listen to me jabber up here. But these last ones should be fun. So, electromagnetic waves is going to be the last one. And you know what? For the sake of my data, let's see if WPA2 works or if it's just going to drop the whole. Let's see what happens to the stream. Yeah, maybe it's working. I'll check in a second and see. Good job. My phone was actually getting a little toasty from that. So, there's some physics there. There's current going through the phone. The more current that's going through it, the more power. Current is I squared R. Set resistance, more current means more power, which means more heat produced. There you go. Now you know why your phone gets toasty. It's literally more current inside your phone. Oh, what a good connection. Anyway, electromagnetic waves, light, everything to do with light. So we're going to first start off with what is light. You may think you know what light is, and some of you are going to have different levels of knowledge, but it is far more than most people realize. Case in point, that Wi-Fi signal, that's light. And that Bluetooth, that's light. When you call someone, that's light, the signal is light. Obviously the projector is light. Any wireless signal is light. Every single wireless signal you ever use is light. Which is something people don't realize. Every single one of you in this room and online are emitting light right now. It's called infrared light. Can't see it. It's light. X-rays, most people know is light, stuff like that. But light is far more than you realize. It's so many more things than you realize. And so light, the word we're going to use for light is electromagnetic waves. And we can see why this is the last thing that we're covering. Just break that into 2 words, electro and magnetic. Light is an electric field and a magnetic field. We've learned about electric fields. We've learned about magnetic fields. Light is the combination of the 2. So, let's do it to it. All right, so yeah, we're going to talk about how light is an electromagnetic wave, what it is, how to characterize it, so wavelength, frequency, amplitude, the electromagnetic spectrum, how light reflects, and how light refracts, which is bending when it goes from one material to another. So what is light and how does it behave, basically will be the name of the game for this. Lots of really, really interesting stuff. So we need to remember electric fields, because electromagnetic, we need to remember magnetic fields. Currents, a little bit, and we definitely need to remember what energy is. Not in any super fancy sense, but just remember energy exists and light has energy. And you can use it to transfer energy from one location to another. All right, so light is an electromagnetic wave. That's just kind of boom, statement right there. It is an electric field and a magnetic field that oscillates. That means goes up and down. So at some spot when light passes by, you get this electric field that you can see kind of down here, where at some spot it gets larger and then it flips and it goes down, and then it goes up again and it goes down. So if you like measured the electric field at some spot as light went by, you would see an electric field arrow getting bigger and then shrink down to zero and then start going downwards and then go up. And then the magnetic field is exactly perpendicular to that, doing the same thing. So it's an electric field and magnetic field that are kind of in sync with each other, that grow and then shrink and then flip directions and grow and then shrink and then flip directions. All light is this. The only difference between the types of lights is how stretched this wave is. If you make this wave really, 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 really like compressed, so we're going to learn what wavelength is, but for now, just know it's between these two peaks. That's one way of doing it. If I squish that wave together, really squish it to like as much as I possibly can, we get a gamma wave, which is the ones that we'll learn come from nuclear bombs. And if you really stretch that wave all the way up to meters, we get radio waves. All light is the same thing. It's just this. It's just a matter of how far apart those waves are. How quickly that field goes up and down. When it goes up and down really quickly, that has a lot of energy, and that's X-rays, gamma waves, stuff like that. When it takes a long time for that, I say long, light's all fast. It happens quick no matter what. But relatively, when it takes longer, that's a radio wave. The faster it flips, the more dangerous it is to you. The slower it flips, the safer it is. And so we'll talk about those categories. But every single wireless signal is light. Already mentioned that. So our first equation here, it's nice. It gives the relationship between, so at any point in this wave, if I calculate if I measure the electric field and then measure the magnetic field, and I divide those two numbers, I get the speed of light, which is just kind of a really interesting relationship. And the speed of light, watching a video today, it made this argument that it's probably one of the most important constants that we know of. The speed of light governs a lot of things. So we're going to be talking about a good amount. The speed of light is 3 times 10 to the 8 meters per second. 3e8, that's 3 times 10 to the 8. Always good to kind of see these numbers, because sometimes we see the scientific notation and we forget what that is. So that's a 3 followed by 1, 2, 3, 4, 5, 6, 7, 8. So it is 300 million meters per second. And something that, again, light is super interesting in a lot of ways, but this number is really interesting. This is the speed limit of the universe. It is literally impossible, as far as we currently understand. You can always put that little asterisk next to anything I say in this class. As far as we understand it, nothing can go faster than this. Does not matter what rocket you put on something, doesn't matter how small the thing is, doesn't matter what you do. You cannot go faster than this, as far as we currently understand. So like all the sci-fi stuff, FTL, that stands for faster than light, we currently have not done that. There's some ideas of ways to do that. None of them have been proven. There's possibly, people mention wormholes and bending space-time, whatever. None of that has been proven. There's ideas, but none of them have been proven. And this light, this is the speed of all light. Radio waves, this is how fast they travel. X-rays, this is how fast they travel. The microwaves inside literally your microwave, this is how fast they travel. Bluetooth signals, this is how fast they travel. This is why we use it for wireless communication. Nothing is faster than light. So if you want to transmit data as quick as you can, you use light. this is one of the arguments. So if you are aware of the Starlink satellite network, so SpaceX putting all these satellites up there. These satellites communicate with light. So traditionally, internet is done through a lot of cables. There's a lot of cables. Fiber optics, that is light. That's cables that use light to send it. Those are really fast. But a lot of your internet signals passes through wires, pretty much all of it. There's literally a giant wire going across the Pacific Ocean to transmit internet signals. Some of it is wired, so like your phone, that obviously there's no wires plugged into it. But the reason Starlink works, the way you can communicate with people halfway across the world, is it uses light. So it transmits the data up to those things, and then they kind of send wireless signals across them. And even though these things are in space, things are far apart, other side of the world, super quick. This is one of the reasons they're in low Earth orbit. If you can shorten that distance, you shorten the time. It's just a simple physics equation. Distance equals velocity times time. Your velocity is the speed of light. Your distance is however far apart they are. Do the quick math and you can get the time it takes for that signal to travel. So, the reason there's so many of these satellites up there, you need line of sight. You can't bend light around the Earth. So you need a bunch of these satellites that all have line of sight of each other. Otherwise, you don't get a signal. Light, super interesting. All travels this fast. I won't get into too much of it, but no one in this room should end up taking physics 3. So there is something called relativity, which says weird things happen when you approach this speed. So I told you it's impossible to get to this speed. You're like, the neat thing is, what if I just, if you keep putting your foot on the gas? Well, okay, let's go to space. If you have a rocket with a rocket engine going, it will speed up and speed up and speed up and speed up. There's no drag in space. There's no air resistance. So, the question is, if I just keep a rocket going forever, shouldn't it go faster forever? Like, that's a logical statement. But the weird thing is, when you get close to this speed, really weird stuff happens. Your length, so like if someone saw you're traveling near the speed, your length would actually look smaller than you are. It's called length contraction. So it looks like you're smaller, which is weird. And like measuring it wise, if you could somehow measure it would be smaller. Your mass, your relative mass also goes up, which is weird. If you could somehow if someone else could measure your mass when you're traveling that fast, your mass gets really high. And if you remember Newton's second law, F equals ma, if your mass goes up, your acceleration goes down. And that's why your acceleration will actually go down, because your mass will go up, which is weird. Even more weird than that is someone saw a clock on your spaceship. So on the spaceship, to you, everything seems normal. Your mass seems normal, your length seems normal, time seems normal. For someone observing you, they would see those things change. They would see the clock. They would see you moving in slow motion. So that's a really weird thing. And this has been proven. This is not like science fiction stuff. This is like well proven. That clock, you would actually see the person moving in slow motion. So if that person experienced, say I was on that spaceship and I felt like 10 years passed, for everyone outside that spaceship, let's just say 20 years passes. Really weird. But this is actually proven, and GPS satellites, for their precision, have to actually account for this. They're not quite going really fast near the speed of light, but they're going fast enough that for the precision needed for GPS, they actually have to account for this time, because the satellites are going fast around the Earth. So they actually have to account for this time. It's called time dilation. Cool stuff, weird stuff. Sounds like science fiction, but it's totally like, that stuff's proven pretty strongly, as much as anything I guess can be. Light, cool stuff. Can't go faster than it. Light travels the same speed kind of everywhere. All light, no matter what kind of light it is. And it's this electromagnetic field. It's really cool, really interesting. How do you make these? How do you make light? There's some easy examples. If you make something hot, it's going to make light. But that's not how we make radio signals. That's not how we make, like your phone, when you call someone, how does it make this light? How does it make these microwave or radio signals, depending on it? So for an electric field, we'll kind of look at each one individually. We actually know enough for you to figure out how these are made. So remember, electric fields are made by charges. So at some point in this picture, it's really hard to see here, but this end is negative and this end is positive. So this is a nice little review. Remember, electric fields point away from positives and they point towards negative. So originally, you get an electric field that's pointed up. Well, let's move those charges around. If I move those charges around, let's just say I start with like 3 negatives up here and I start with 3 positives down here. If I kind of move them around, move some of those negatives to the bottom, that'll cancel out one of these and that'll make a field that's a little bit weaker. And then I make, a little bit less and I make a field that's a little bit weaker. And eventually, no charges, so I no field. And then I start putting the negatives down here. And I start putting the positives up here. Oh, now I've got a field going the other way. And then I add charges. And I make the field going the other way. And you can see how we can make an electric field that goes up and down. Great, that's my electric field. Well, while I'm doing this, remember y'all, if you have current moving, you're making a magnetic field. So if you're moving charges, that's current. If you have current, right-hand rule, you're making a magnetic field. So in the bottom of this picture here, as those charges are moving, you can do right-hand rule and see that we're making a magnetic field. The more current, the quicker I make that current flow, the stronger the field. At some point I slow down the current, makes a weaker field. At some point I make the current go the other way. Now my magnetic field's the other way. So at the same time you're moving those charges and getting a different electric field, you're getting a different magnetic field. And this is how every wireless transmission works. It's moving current. So your phone, how does it make a wireless signal? So the antenna in here is literally just some wires, and it moves current back and forth. And that makes a signal. Depending on how quickly you move that, depends on the frequency, depends on what wavelength of light you're making. All those radio towers, that's all they're doing. They're moving current up and down, and that's how you make a signal. Depending on how quick you do that, depends upon the kind of light you're making. So, we had to understand, I couldn't tell you how these things work until we get to the end of the class, because we had to understand all this stuff together. And then, how do you pick up this signal? Well, when this electric field hits your phone, it's going to move charges. And so, it's literally just going to do the exact opposite. The moving charges make the field, the moving field's going to move charges in your phone, and you can pick that up. So an antenna and a receiver are the exact same thing. They just work, but like one of them's off and it picks up the signal, the other one's on and it drives a signal. So like your car's antenna, I think most cars still have them. It's literally just a piece of wire. And when the field hits it, it moves current one way, and then the field goes the other way, it moves current the other way, and you're just measuring current. That's all your wireless signals are doing, is measuring current. So, interesting stuff. I think it's really, so much of our society relies upon this, and 99.5% of people, probably still conservative, have no idea how wireless signals are generated. Everyone relies on their phone, like very few people in this world don't rely on their phones for calling, for internet, for all that stuff. And as far as most people are aware, it's a magic box that when I do things, it does things. But now you actually understand it's all based, this is why someone, whether it's you or anyone else, someone needed to understand how this worked for our society to get to where we're at. Which may have been obvious, but now you kind of can see what that something is. And you all understand it. You all have enough knowledge in this class to understand this stuff. Even if it doesn't feel like it right now, you do. You just spend some time in this, you can understand it. If right now it's not making sense, that's okay. Okay. This is another interesting question. So if the sun suddenly turned off, this is the first problem in your all's problem set. We would not know it until the light stopped reaching us. How long would that take? So let's just we think that when we look at the sun, we're seeing it as it is right now. We're not. For you to see the sun, you have to just think a little bit further. What does that mean? It means that light from the sun had to travel through space and eventually reach your eyes. You can't see something unless the light from that thing reaches your eyes. So every single object in this room, you can only see it because light bounced off it And after that light bounced off it, it hits your eyes, eventually. But until that light hits, and that's why, again, this is going to sound like an obvious thing. It's not obvious when you're a baby. None of you can see my backpack that's behind this desk. I didn't do anything magical. There is light coming off this backpack. It's just not hitting your eyes. Through the magic of making it so now the light hits your eyes, you can see it. It's like, obviously you all can't see it when it's behind the desk. But physics-wise, why not? Because the light has to reach your eyeballs. And it has to, so the light from the ceiling hits my backpack, bounces off it, hits your eyes. You can't see the backside of my backpack because the light, how's it going to reach your eyes? It can't like bend around it. So anywho, the sun's the same way. For you to see the sun, the light has to go from the sun to your face. None of you can see the sun in this room right now. Maybe if you're online, you have a window nearby. We do not. So if the sun blew up, we'd have no idea here as far as light is concerned because it can't reach our eyeballs. So anywho, light's got to travel. But really straightforward calculation here. So how long would that take given that the sun is 1.5 times 10 to the 11 meters away? That's a huge number. You take that decimal place and you move it 11 times to the right and you're going to get how big that number is. Don't even know what that number is called. It's a big distance. So what's given? We have distance. This is actually a physics 1 problem, but in the easiest sense. I don't want y'all to, like, sometimes people hear physics 1, they suffer some PTSD from that. It's the easiest type of physics 1 problem. So my distance is that. There is something else we know, but we'll figure that out eventually. If you know distance and you want to figure out how long it takes to travel, well, we do know, and actually I'll put that here, we know how fast light travels. So the velocity of light, all light, doesn't matter what kind, is 3 times 10 to the 8. We are solving for time, and this is a good, see if you all remember, give you all like 30 seconds. What is the relationship between distance, velocity, and time? It's a very simple relationship, nothing fancy, but see if y'all can remember it. If not, that's fine. You do not have to have it memorized for this class, but it is a very simple relationship. So, it's a really simple relationship. It's x equals vt. Distance equals velocity times time. Really easy to remember this one. If your car is traveling 30 miles per hour, how far do you travel in 2 hours? 30 times 2. Take your velocity, multiply by the time, you're going to get how far it goes. But in this case, we are solving for t. So we put in our numbers. So 1.5 times 10 to the 11 equals 3 times 10 to the 8 times time. So we're just going to divide that on over. And what I really want to make certain we recognize here, it's going to be very obvious, this time is not 0. In fact, it's a far away from 0. It's not even a decimal. So this time is going to come out in seconds, because all our other units are in, base units are in seconds. So this is not 1 second. This is not even 10 seconds, not 30 seconds. This is going to be 500 seconds. That's how long it takes for the light from the sun to reach here. And so to make that a little bit more like meaningful, one, we can convert that to minutes, just divide that by 60. So 8.33 minutes. To make that a bit more meaningful, that means if the sun blew up, you would not know for 8 minutes. If the sun blew up right now, it would take 8 minutes for us to realize that. Because again, think through how would you know the sun blew up? You would have to have information. How do you know anything about the sun? You see it. What does that mean? So that literally means the light, when the sun blows up, the time for that explosion, the light from that explosion to reach Earth will take 8 minutes. So this has all sorts of interesting takeaways here. One, space is huge. Light is the fastest thing in the universe, meaning you literally cannot get to the sun faster than 8 minutes. Nothing can get to the sun faster. Information cannot travel faster than this. This is the speed limit. To that end, think about what that means across the solar system. So we often hear like stuff about space missions to Mars and all that kind of stuff. Let's just say that Mars is on the other side of the sun. That means wherever Mars is, if it's on the other side, it's going to take longer than 8 minutes for any signal from Earth to travel to Mars. So say you're trying to land a spacecraft on Mars. Depending on where it's at, even if it's close by, I don't know what the closest is, but let's just say it's like 3 minutes or something. Any signal you send, say you got your lander coming down, say you're like, oh crap, there's a rock coming down. Yeah, when you received that signal, that was 3 minutes ago. It's very likely they already hit that rock. So you cannot remotely control spacecraft when you're landing on other planets. You can't manually control it from Earth at least, because there's a time delay. So whatever you see on a video feed, that's minimum 3 minutes, and that's like assuming that's the closest it is. It could be more than that. And obviously imagine you're driving your car and there's a 3-minute delay between what you see and what's actually happening. Yeah, no one can drive a car with a 3-minute delay. Maybe if you're going like a centimeter a second, maybe, but even then. So that's really interesting. So that's why it's so hard to land on other planets, because any landing has to be done. The lander has to be able to do it without us. Whatever computer code is written, better be able to take care of it, because we can't do anything about it. Yeah.
Is it different from the moon?
So the moon is much closer, but there's still a bit of a delay. Let's actually look it up real quick. I don't remember the exact distance between us and the moon. So distance from Earth to moon in meters. So that's 384 million meters. I think it's 1.5 seconds. So if we just take 384 million, yeah, it comes out to a little over a second. So 3.84, 1, 2, 3, 4, 5, 6, 7. Scientific notation, 1, 2, 3, 4, 5, 6, 7, 8. So let's just make a new slide and plop that on here. So the moon, that distance is 3.84 times 10 to the 8 meters. And that's pretty much always the same distance. The moon's in roughly a pretty circular orbit, so that's pretty constant. Speed of light is still 3 to the 8. So if you want to calculate the time, you just do those two things divided by each other. So 3.84 E8 divided by 3 E8. The E8s cancel, which is nice. So 1.27 seconds delay. But that's similar. Like if you want to land something, 1.2 seconds, maybe they could do it manually, but that's a pretty long delay. For anyone that plays video games, you know there's that millisecond delay with things, and that kind of gives you a sense of how that would be a 1,270 millisecond delay. Which if anyone plays video games, that's like hard to do anything well. That's a long time. A lot can happen, as weird as that sounds, a lot can happen in 1.27 seconds. So they can do some adjustments more with the moon, but still somewhat limited. Let's see. And then the interesting there, if you send a signal, whatever happens will then take another 1.2. So if you send a signal, the round trip time is going to be 2.5 seconds. So also makes it complicated. Yeah.
How do you think they control the Mars rover?
So they can control it, but so there's some autonomous stuff going on, but they also map out kind of the paths. So once it lands there, they can kind of get a sense of what's going on. They have a lot of satellite imagery and things like that. So they can kind of give it some instructions, go here, go there. But they do a lot. They're very patient with these things. They do not rush into any move, because if anything happens, obviously they can't fix it. So they really carefully map out their stuff. And generally they also try to land in an area that doesn't have many rocks in it. 1, to avoid the risk of running into things, but 2, also for rovers so they don't run into as much stuff as well. But yeah, they carefully do it, and it may be one of those go this far for a second, wait, see where we're at, go a little bit farther, see where we're at. They go very carefully with any space tech for that reason. Better to go slow and careful than to rush things and run into stuff and break something and you can't do anything about it. Yeah, it's a good question. So, yeah, space is huge, y'all. This also connects to the idea of a light year. So you've heard probably the phrase light year. Let's just go ahead and calculate what a light year is really quickly, because it's something you can do. It's nothing fancy. What is a light year? So, a light year is the distance you don't need to know this, but for funsies, distance traveled by light in 1 year. That's all it is. It's a distance, even though it sounds like a time. So if you want to calculate how far a light year is, you take the speed of light, 3 times 10 to the 8, you multiply it by the days in a year, the hours in a day, the minutes in an hour, and the seconds. So all we're doing is figuring out how many seconds are in a year. We take 3e8 times seconds in a year, because 3e8's in meters per second. So we plug that in, 3e8 times 365 times 24 times 60 times 60, and we get 9.46 times 10 to the 15 meters. The reason I mention this, 1, this is such a big number you can't even imagine it. 2, the nearest star is light years away, meaning I think like 4 light years, meaning if you could travel the fastest speed in the universe, it would still take you 4 years to get to it. And we cannot travel the fastest speed in the universe. So this has all sorts of interesting things, makes you realize, and that's the closest star. The universe is a lot bigger than that. Really gives you a sense of scale of this universe. You are closer, ratio-wise, to the size of an atom than you are to the size of the universe. So that also puts some things into perspective. But sometimes good, I don't know, it makes you wonder why and all that kind of stuff. And, take that as you may. But it's a big universe, y'all. It's so big. There are things so big in this universe, like the universe is so big you can't imagine it, and atoms are so small you can't imagine it, and we're not even in the middle. We're closer to an atom than we are to the universe. So you can't even say we're dead in the middle. No. We're way closer to an atom than the universe. Which is just wild. So cool stuff, y'all. Light's cool because it's a speed limit and it governs kind of everything. All right, this slide looks crazy. Don't freak out about this. This looks worse than it is. Light carries energy. If you want to measure this energy, we're going to kind of measure it based on the meters squared. Because think of like the sun shining on the earth, or the bigger your surface area, the more energy you collect. So we have to account for that. You can't just say what's the energy. You can get the energy of the light, and we'll get to that for 1 photon. But in practical application, think of like a solar panel. The bigger your solar panel, the more energy you collect. So this gives you the energy per second per unit of area. More area will mean more energy. And these equations look all sorts of crazy, but they're using stuff that we've actually seen. Everything in these equations, none of these are new variables except for I. And I is just energy per meter squared. Everything else we've seen. Epsilon naught, we've used that a couple times. If you all remember the capacitor, this is in that capacitor equation. 8.854 times 10 to the minus 12. Mu naught, we used that a heck of a lot on the last test. Permeability of free space, 4 pi times 10 to the minus 7. E naught is literally just how the max strength of the electric field. B naught is just the max strength of the magnetic field. So all these variables, the only new variable is this one called intensity, which is the energy per second per area. And if you look at the units for that, energy per second, hey, we've seen that word before. It's power. So if you all look at the units, so energy per second, that's power, which is measured in watts. Unit area, that's meters squared. Look at the units here. The units are watts per meter squared. Power per unit squared. So this is how much energy, if you go stand out in the sunshine, the sun has a certain intensity to it. Certain amount of energy it's transmitting every second per meter squared. And, you know, you can harness that in all sorts of ways. You can literally just put something out there and it'll get hot. Or if you have a solar panel, you can convert it to electricity. We are not, I can say how I know how solar panels work. We're not going to necessarily go into them too much because they have to do with, you have to understand a little bit about semiconductors and things like that. So who knows? Maybe at some point I'll mention something about them. But how solar panels work, it's not based on heat. It's a little bit more complicated than that. So I mentioned that just like solar panels are a little bit more complicated than just gathering heat. But who knows? At some point maybe I'll mention that. But they do take this energy and they convert it to electricity through a certain path. So anyway, all these equations, so fancy, but they really just boil down to all of these are just variations on the same thing. And what they come from is this, remember C equals E over B? So you just do a bunch of substitutions to get all the other ones. C, we just said, was E over B. Or, let me clarify, let me double, triple check that because yep, C is E over B. So based on various substitutions, we can get these various things. All right, anyway, let's do a really simple example of this that is honestly not going to use any of those equations. Okay, let me rephrase that. The first part's not going to use any of those equations. The second part's will. All right, so on the highest power setting, a certain microwave oven projects 1 kilowatts of microwaves onto a 30 by 40 centimeter area. What is the intensity? Let's just start there and show you all, kind of connect what is intensity idea-wise. So kilowatts. What variable does that go with? Power. Watts is power. So 1 kilowatt, we do need to convert that, so that's going to be 1,000 watts. And we have a 30 by 40 centimeter area. Let's actually just go ahead and get what that area is. We're going to need that. So the area, and let's do our unit conversion sooner than later, because when it comes to centimeters, if you try to do it afterwards, you're going to run into some problems. So 0.3, and you know what, just to make it obvious what's going on here, 0.30 times 0.40, 30 centimeters by 40 centimeters. I don't want to make a silly error here. Obviously 3 times 4 is 12, but because of the decimals, that's going to do some funky stuff with moving them around. Actually it wasn't as bad as I thought, but better safe than sorry. So I have power, I have area. Part 1 is literally, so what's the intensity? And it's actually not going to be any of the equations I showed you. But if you look at what it says, what is the intensity in watts divided by meters squared? That's exactly what we're going to do. We're going to take our wattage and divide it by our area. That's it. So it's not actually one of those equations, it's literally the definition of intensity. Power per meter squared. So what's our equation for intensity? Power per area. That is the fundamental definition of what intensity is. So step 4, intensity equals 1,000 divided by 0.12, and that's just a number. It seems deceptively simple, like, oh, just be like 12,000. No, again, always better to plug things in a calculator. This comes out to 8,333.33 watts per meter squared. All right. There we go. We got our intensity. Now it says calculate the peak electric field strength in these waves. I'm not actually going to spend the time on this. I'm just going to help you all identify what equation to use for it. Once you have intensity, so I'm going to copy and paste all of this stuff into a new slide to give myself a little bit more room. So in the later ones, and I'm going to give myself a little bit, we'll leave that there. So for part B, we are solving for E naught equals question mark. For part C, we're solving for B naught equals question mark. And it's just one of those classic, y'all. What do we have? What do we need? And we go back, and I'm actually going to copy and paste this because I do not want to try to remember all of that. So if we just look at this and make it actually so you can read it. It's classic, y'all. Choose the one that has what we have. So if you're solving for E naught, well, we have I. We know C, that's just 3 times 10 to the 8. We know epsilon naught. That's just a number. It's 8.854 to the 10 to the minus 12. So if you want to solve for E naught, we just use this first one. You have everything and it's just some algebra. Nothing too fancy there, just math. Physics-wise, nothing too much to say about that. So if you want to solve for E naught, you got I, you've got C, you've got epsilon naught, easy peasy. You want to solve for B naught? We're going to use these two instead. You have I, you have C, you know mu naught. And it's just a plug and chug situation. So to make that a little bit more clear, so I average will equal C B naught squared over 2 mu naught. And it is literally just a plug and chug. Okay, you have to do some algebra, but nothing too fancy there. But I wanted to introduce this idea of intensity. Honestly, I'm going to double, triple check this, so I will check before next class before I can quote you on this. This is not a super important skill that I care about, these equations. What I do care about is that you know that when light is emitted, the energy you collect from it depends on how much area. Which, again, hopefully obviously makes sense. The bigger the solar panel, the more energy you collect. When you go outside, a big black tarp is going to collect more energy than a tiny black sheet of paper. That's the main idea that I care about you all knowing. That the sun is emitting energy every second, and the more surface area you can collect of that, the better. If you want to harness that energy. What is also interesting about this is this energy spreads out from the sun, so the farther away you get, the less you get per meter squared. Makes sense. There's only so much energy. The farther away you get, the more it spreads out. But, okay, this is definitely super important. So whatever, there's a bunch of mathy things. This is really important. This is stuff you 100% need to know. Frequency and wavelength are very important ideas. This is critical to understanding light. So wavelength, I think, is the easier one to start with. Now, I put it as the distance between peaks of a wave, but honestly, a better way to understand wavelength is the distance between two identical spots in a wave. So this wave repeats itself again and again and again. It just repeats up, down, up, down, up, down, however far it travels. And just think what the word wavelength means. It's the wave's length. The word means what it says. But say I want to measure the wavelength of some light coming from the sun to the earth. I'm not going to say the wavelength of that light is from where it started in the sun to when it hit the earth. That's kind of a silly measurement because it's just not very useful. So what we do is we say, what is the length of one part of the wave that repeats itself? So peak to peak is easy to see. So if we look at our picture here, we can see that this spot, the peaks, when a peak happens again, the distance between those, that is one full wave. So like if I draw this, that is going to repeat itself again and again and again and again and again. So if I kind of like overlay this part, if I just keep repeating this, that's what the wave's going to look like forever. You could draw what this wave would look like infinitely far with just that piece of information. What I also want to point out is that wavelength is the distance between the troughs, because those are the two, they're identical. The bottom and the bottom. Distance between those, that's also wavelength. The wavelength is also the distance between this spot here in the middle going up and this spot here, the middle going up. Notice that all of these are the same distance. Oh, the wavelength is also, there is an infinite number of ways, y'all, to measure wavelength. Between these two spots, you pick two identical spots, measure the distance between them, that's wavelength. Pick some spot, find the next spot that's just like it, measure the distance, that's wavelength. Doesn't matter what spot you pick, as long as the next spot you pick is identical to it. You pick the top of the wave, the next spot's the top. You pick the bottom, the next spot's the bottom. If you pick the middle, you have to check is the wave going up or down. Because notice that when I pick the middle, so when I pick this middle going up, I did not say the middle going, that's identical. Because in the beginning it's going up, at this spot here, it's going down. Those are not identical. So it's the next spot that's in the middle going up. All right, so wavelength, very important. Wavelength is the distance between two identical spots measured in meters because it's wavelength. The symbol for it is lambda. So that's Greek letter lambda, lowercase lambda. Part of this class, you all have learned a whole variety of Greek letters of the alphabet at this point. So how do you draw lambda? It's a pretty satisfying one. You draw a little kind of arch like this. So almost like a kind of a hump, almost like a piece of a wave. Maybe that's why they chose it. I don't know. And you give it a leg. I mean, part of this, as silly as it sounds, I do remember learning these letters for the first time and having to like get used to drawing them. So sometimes it's helpful to, so yeah, this little kind of, this is how I draw it, and then a leg. So that's lambda, lowercase lambda. So lambda, great. Wavelength, awesome. Frequency is what it sounds like. It's how frequent the wave is. How many waves do you see a second? You can think of it like if you're watching ocean waves pass you by. If you calculated if you counted how many times you saw like the peak of a wave pass you by, and you divided that by seconds, how long it took, that would give you how frequent those waves are. If 5 waves passed you in 1 second, I have a frequency of 5 hertz. If 2 waves pass you in a second, 2 hertz. If half a wave passes you in a second, half a hertz. The unit is hertz, like the car rental company, so Hz is the shorthand for it. Seconds inverse and hertz are the same thing. So this is waves per second. Waves is not really a unit, so we don't like there's not a unit for counting how many waves. Anytime you count something, there's not a unit for it. What's the unit for how many cats someone has? 3 cats. But it's not really a unit. Anytime you count anything, it's not really a unit. So what this ends up turning into is just 1 over seconds, and we just call that hertz. So now anytime you all have seen hertz, and there is so many places you all have seen hertz, your Wi-Fi signal at home is, either 5 gigahertz or, what's the other, 2 point something, but 2.4. That's the frequency of the light that your Wi-Fi signal is generating, ballpark-wise. So remember, all light is meant like different waves, different frequencies, and we're going to find the correlation between that wavelength. They're correlated with a really simple equation. So the way this stuff works, your Wi-Fi at home, when it says a 2.4 gigahertz signal, there's actually a range there, and everything in your network gets a very slightly different frequency. What can happen is if you and your neighbor are kind of using the same frequency, you'll get interference between those. And they call those channels, and that's actually a troubleshooting thing. If you're constantly having troubles with your Wi-Fi, one of the reasons can be that you're using the same frequency of light as your neighbor is, and they can interfere with each other. And there's ways in your router to change the channel you're in, slightly shift your frequency to one that's not being used by people around you. So that's interesting. But yeah, you'll see it all over the place. Hertz, like so many signals, that's how you define them. Here's the relationship, really simple. The relationship between wavelength and frequency, so all light travels at the speed of light. Doesn't matter what kind. So, the speed of light equals wavelength times frequency. As wavelength goes up, frequency goes down. As frequency goes up, wavelength goes down. C is a constant, so whatever happens to one of them, the opposite happens to the other. If I double the wavelength, I have to half the frequency. So you can define any wave by either its wavelength or frequency. We tend to use frequency. I don't know why. Maybe just, I don't know, someone decided. And we are assuming light is in a vacuum. That's going to kind of come into play later, which is all sorts of funky, but we'll get to that funkiness when we get there. All right, and we will finally throw some clicker questions in. I feel the need to give you all something for being here. All right, and I'll even probably make up a couple extra just to make it doubly worth, because we haven't really had any, which is very sad. All right, sure. So let's just make up one right now. Clicker question. I haven't even told you about these. How does the speed of your Wi-Fi signal compare to the speed of light from the sun? Wi-Fi greater than sunlight, sunlight greater than Wi-Fi, same, not enough information. You may be like, what the heck? Where's this question coming from? If you're not sure, take a guess. How does the speed of your Wi-Fi signal compare to the speed of light from the sun? And then we'll do a few more to kind of close out our class today. A few more questions talking about wavelength and frequency. Ooh, I am getting different answers. I'm glad I asked it. All right, we'll go to like 50 seconds. One of those, go with your gut. Worst comes to worst, it's wrong, and you still get 75% of the points, and nothing really changed in your life. All right, we'll close it out in 5, 4, 3, 2, 1. And so the real kicker here, y'all, if you're like, how the heck was I supposed to know the answer to this? It's all light. It's all light, and all light travels the same speed. A Wi-Fi signal is just light. It's all light. Wi-Fi signals, radio signals, the stuff that your microwave uses, those are microwaves, which are kind of light. It's all the same speed, 3 times 10 to the 8. So what's the speed of the Wi-Fi signal? 3 times 10 to the 8 meters per second. What's the speed of this? The light from the sun? It's emitting all the signals. It's emitting same frequencies as your Wi-Fi is even. The sun emits all the, not just visible light, but all the different types. Well, all of that light, who cares what type it is? It all goes 3 times 10 to the 8 meters per second. X-rays, 3 times 10 to the 8 meters per second. All light. All right, now, this is kind of getting more so to the thing I just gave you all with the equation. What happens to frequency as wavelength goes up? And the equation I just gave you all was C equals lambda times F, where lambda is the wavelength, and frequency is F is the frequency. Same thing, we'll go to just 50 seconds for this because there's no math involved here. You can make up numbers if you really want to, but go with your gut. 5, 4, 3, 2, 1. All right, so C is a constant. It does not change. So if we let's say the frequency doubles. Just make it up. Who cares what happens? So let's just say it doubles. I still need the left side to equal C. So how do I get rid of that doubles? I have to half the wavelength. Those will cancel and make it so that I still get C. If frequency goes up, wavelength goes down. They are opposites to each other. And so what does this look like in application? So this is a wave with a large wavelength. This is a wave with a short wavelength. So this one's wavelength is up, but its frequency. This one has a smaller wavelength, but a higher frequency. This one has a bigger wavelength, but a lower frequency. They're both traveling at the same speed. They're both traveling the speed of light. These waves are both zipping by. And to that end, remember, we're going to learn eventually, higher frequency waves are more dangerous. The higher the frequency, the more energy it's going to have. The more energy it has, the more dangerous it is to you and anything else, really. Just like a hot stove is more dangerous than something that's not, something that's warm. I don't know. More energy, if it hits you, it's bad. A car with more energy that hits you ain't going to go well for you. So we're going to learn eventually this has more energy. And the reason, and conceptually why, it's wiggling things around really quickly. You can kind of think about that would cause the charges in your body to wiggle around really quickly. You could think about why that would be bad. Everything's made of these charges. It could cause things that wiggle quickly that's all heat is. Heat is just things wiggling really quickly. So that's another example. All right. Yeah, I'm going to give this one to you all. We're just going to think in previous me. What is the ratio and frequency of violet light to red light? And I'm going to straight up tell you all, I'm either going to do 400 divided by 650 or 650 divided by 400. Question is which? And the way to think about that, we just talked about it. As frequency goes up, wavelength goes down. As frequency goes up, wavelength goes down. So should violet light have a larger frequency or a smaller frequency than red light? That's the way to think about this question. Don't get too caught up in the math. More think about it conceptually. A violet light has a 400 nanometer wavelength and red light has a 650 nanometer wavelength. And so the question is, if we look at our answers, we have the frequency of red light. If I multiply by the violet light by a number bigger than 1, I get a bigger number. If I multiply by a number smaller than 1, I get a smaller number. So, should red light have a larger frequency, or should it have a smaller frequency? And then do the division that makes that happen. Should red light have a larger frequency or a smaller frequency based on this? So as weird as it sounds, this kind of falls into the conceptual thing. Because if you try to do you could do the math and it's just going to take you more time. But if you think about it conceptually, it's not too bad. Will it have a larger frequency or a smaller frequency? And then what math operation do I need to do to make that happen? Whatever that may be. So this one, we're going to give some time too so you can process through it. Then we'll do one more question after this. Call it good. All right, so I'll go to like 220, 15 more seconds. All right, we'll close it out in 5, 4, 3, 2, 1. Okay, so let's just look at these. Let's just think through that first step. Which one should have a larger frequency? They're opposites, remember y'all? Whatever happens to wavelength, the opposite's frequency. So violet light has a smaller wavelength, so that means it has a larger frequency. Violet light, the wavelength of violet light is smaller than the wavelength of red light. 400 is a smaller number than 650. So then the opposite will be true of frequency. The frequency of violet light must be bigger than the frequency of red light because they're opposites. So we just look at these numbers and we say, which way is that going to work out? 650 divided by 400 or 400 divided by 650? So the frequency, and I will clarify here, these are all in red light. So the frequency of red light needs to be smaller. So let me actually flip these just to make it match kind of our answers. It doesn't change the rules. The thing I told you all is still the same. Everything, I'm just flipping it to make it more match up with what I wrote down here. Well, there's no typos here. So the frequency of red light is smaller. The frequency of red light is smaller because that has a bigger wavelength. Red light has a bigger wavelength than violet light. So how do I make it have a smaller? I take 400 and I divide it by 650 times the frequency of violet. Now, you can kind of work this out a bit more methodically, mathematically, and all that kind of jazz. But honestly, conceptually, in my opinion, this is the easier way to explain it. If you remember that whole inverse thing, and you can do the math. You can literally calculate these frequencies if you want. That's the way to brute force do this. Calculate the frequency of violet, calculate the frequency of red light. You can prove this to yourself. But what this ends up turning out to be is B. Hey, which is pretty good, y'all. Again, we are mostly split between the first two options, which way to divide it. Red light needs a bigger frequency. Sorry, smaller frequency, because it's got a bigger wavelength. Great. I'm going to put this up just to answer it. Really obvious, the answer is D, y'all. I got light with a certain wavelength. I just want to give you all free points to make certain, because I didn't have many of these. I'm not trying to necessarily extend the class. I just want to give you all some extra points. I got light with a wavelength of 30. I got light with a wavelength of 50. How do their velocities compare? They're the same. It's light. Who cares? The answer is D. Make certain you pick D. Again, only put this up here just to make sure and give you all some points because I didn't ask as many as I normally do. All right, y'all, light. Cool stuff. I enjoy this topic a lot. Conceptually, very, very interesting. I'll leave this kind of poll up, but I'll go ahead and close the stream and all that. And any questions, comments, concerns, feel free to come on down.